Hey everybody, this is Mr. Walsh, and we are wrapping up our section on periodic trends by discussing the last couple of periodic trends. Just so you know, there are a million periodic trends. There's even an activity that we'll be doing talking about all the periodic trends, but here we're going to finish up Unit 2.6, Unit 2, Section 6, talking about the other two periodic. So the other two periodic trends that we're going to talk about here are ionization energy and electronegativity. Okay, the ionization energy is the amount of energy it takes to remove an electron. You can just pause the video and write that down. So if you have an atom, okay, here's the Bohr model, and you want to remove that electron completely from it, it takes a certain amount of energy. Ionization energy is how much energy it takes to remove that. Okay, and then electronegativity is kind of the opposite of that, and it's the ability of an element to attract electrons when bonded. So if we have, let's say, a carbon atom bonded to a hydrogen atom, these two atoms are kind of fighting over the electrons in this bond. And so are they going to be attracted to carbon more? Are they going to be attracted to hydrogen more? Who knows? But it's a tug of war, and electronegativity tells you who is going to be winning that tug of war for those electrons. So let's talk about ionization energy. And just so you know, the ionization energy and electronegativity is based on atomic radius. So if you're not familiar or you don't know what's going on, go back to the atomic radius video, watch it, and we can go from there. Okay, so ionization energy. Like I said, we already wrote this down, so you don't need that, okay? But, so, remember, with size, it's the amount of protons holding these electrons in, right? So lithium can't hold the electrons as well as carbon because there's more protons holding them in. So, the smaller the atom, okay, the smaller atoms need a higher ionization energy in order to pull the electrons off. So the smaller the atom, the higher the ionization energy. So again, the larger the atom, the smaller the ionization energy. Okay? And so that's true for all the atoms on the periodic table. So francium has the biggest radius, but has the smallest ionization energy. Okay, because it's the biggest radius, it holds on to those electrons less tightly, and so it doesn't take much energy to remove them. As opposed to helium, which is the smallest, okay, and because helium is the smallest radius, it has the largest ionization energy, okay, and so we can, and so what I say is, in a practical sense, it's just the opposite trend, because as one goes up, the other goes down, okay, so which elements have the highest ionization energy? When I get a question like this, I want to refer it back to size because I understand size better than I understand kind of what ionization energy is. And so the highest ionization energy is really asking which one is the smallest element in the group, okay? Smallest radius. And now we can go through and we can look at these in the we have. So again, CNSIP. If I do that, I'm going to go C versus N. Which one is the smaller radius? That's N. N versus SI. N. And then N versus P. N is the smaller radius. So that must have the highest ionization energy. let's see, SBTEBIPO, SB TE, BI, and PO. So we're talking about these, SB, TE, BI, PO. And so again, the smallest one is the one that is the furthest up, least energy levels, and the furthest to the right with the more protons. So this is going to be the smallest one, tellurium. Okay, smallest radius, but has the highest ionization energy. LIBENAMG. LINABEMG. Again, we want the one that's further up, so it's LI or BE, and then we want the one that's further to the left, or further to the right, which is BE. Okay, so we get this. And now we'll do the middle, WNBTAMO. So WNBTAMO. So again, we want the ones that are higher and to the right. So that's going to be MO, molybdenum. Okay, molybdenum. Okay, so now the same thing. Okay, electronegativity. We already wrote down that that definition a couple slides ago, but the idea is that when you have a smaller atom, the more likely the bond between that smaller atom is going to be attracted to it. Okay, so in a practical sense, electronegativity is the opposite of size again. So the larger the radius, the smaller the electronegativity. I don't want to have to keep writing out electronegativity. Okay, that's a 16-letter word that just gets annoying to write out. Okay, and so if you want to see it on a periodic table again, here it is. Okay, so again, francium has the biggest radius, so it has the smallest electronegativity. Okay, smallest, I'll write it down, arrow, smallest. Okay, and the other thing is that now here, look, now we go to F. We don't go all the way. This is, of the elements that react, we don't count the noble gases because the noble gases don't react. So we're going to go up here, we're going to say that F has the smallest radius. Okay. I know hydrogen's over here. Hydrogen's an exception to so many things. But fluorine is the smallest radius, so that has the highest electronegativity of the ones that react. So we ignore the noble gases because the noble gases don't react, and that's on them. We'll just say that. Okay. So now, if we're going to look at this, okay, we have WNBTAMO, W, and what do we want? We want the lowest electronegativity, so we want the biggest size. Okay, so WNBTAMO, so we want the biggest size, so we're going to go down, the one that's down and to the left, so that's going to be TA. PDCORHNI, PDRHCONI. So rhodium is the biggest element. It's the one that's furthest down and furthest to the left. So that's going to be OFSCl. OFSCl. Okay, so the one that's the biggest is S. It's the furthest down and furthest to the left. ALSIGEGA. ALSIGEGA. Again, the furthest down, GA. Okay. So that's electronegativity. Okay, so there we have it. Okay, other trends, but it's all based on the size trend. So make sure you understand the size trend before we do anything else. Okay, everybody, have a great day.